Okay, hello. Now I want to look at chapter 4. Chapter 4 is on amplifiers. So the aim of this chapter is basically for you to understand what is amplification, how are amplifiers used to amplify signals in a telecommunication system. And as for the objectives, you should be able to define amplification, state the basic function of an amplifier, basically, which is to increase signal level, also define gain, selectivity, and bandwidth, and also to look at the type of amplifiers and the classes of amplifiers. So in our first chapter, which is chapter 1, we looked at gain as the increase in signal strength. So in this chapter, we are now explaining amplification as increasing voltage or power, which is increasing the strength of a signal. So when we increase the strength of a signal, which is gain, we're actually doing what we call amplification. So amplification doesn't have to change the frequency of a waveform. The waveform frequency remains the same, but it is the signal amplitude that increases. The general symbol of an amplifier here shows that we've got our input, which can be fed here normally, and then we've got our output, which we can take from that point. So amplifier gain, we already know what amplifier gain is. It's output over input. We can talk about voltage gain, where we say voltage, output voltage over input voltage. Current gain is output current over input current. Power gain, which is output power over input power. We should also know that power is the product of voltage and current. The voltage gain, power gain, and current gain can also be expressed in decibels using those formulas. A frequency response shows the characteristic of our amplifier for given frequencies. So amplifiers do not amplify all frequencies to the same extent. So that's why we need a frequency response curve in order for it to explain how amplification is carried out. Audio frequencies range from up to 20 kilohertz, as shown here, maybe from 10 Hz to 20 kilohertz. So what basically happens is that when you are using an audio frequency amplifier, it can only amplify frequencies below 20 kilohertz. Anything above 20 kilohertz is not amplified. So here we're given a response curve for an audio frequency amplifier, whereby it is amplifying frequencies from 10 Hz up to a certain frequency here, which is not given. Let's just assume it's the 20 kilohertz. So these frequencies within this bandwidth are considered the band of frequencies being amplified by this audio amplifier. So anything above, for example, 100 kilohertz here won't be amplified by this amplifier. We can also talk about the bandwidth of an RF amplifier. This is 774 kilohertz being the center frequency, and those range of frequencies being amplified. So it actually means that this particular amplifier cannot amplify these frequencies, whilst this amplifier cannot also amplify frequencies given by this response curve. So each amplifier has got a particular response curve which depends on the characteristic of that amplifier. So bandwidth, we also looked at bandwidth, whereby is the range of frequencies being amplified by this amplifier. So if you are asked what is bandwidth in respect to amplifiers, it is basically the bandwidth in band of frequencies which an amplifier can amplify. We can also mention that any frequencies outside that band will not be amplified. For example, like 100 kilohertz cannot be amplified using the audio frequency amplifier. So, just like in filters, we consider the -3 dB points as the cutoff frequencies. So, any frequencies with a gain less than -3 dB is actually considered outside the passband, but anything above 3 dB is considered the passband frequencies, or the frequencies we want to amplify. Another important term that we want to look at is selectivity. Selectivity comes from the word select. We want to select a particular range of frequencies to amplify. So, therefore, we say an amplifier that has got selectivity is an amplifier that can only amplify a certain range of frequencies, whilst anything outside that range is not amplified. So in order for us to be able to select frequencies, we need what we call an LC tank. This is an LC tank. It consists of an inductor and a capacitor connected in parallel. An LC tank has got a resonant frequency given by F0 is equals to 1/2 pi root LC. What it simply means, F0 or FR is the center frequency, and then the bandwidth is then calculated by the -3 dB points, or 0.707 if you are talking about amplitude. For example, if this is I maximum, it's 0.707 is where you get the -3 dB currents. So the only difference is that here we are dealing with current, and in that other where we get -3 dB, we'll be dealing with gain. So our inductor and capacitor connected in parallel gives us this property of selectivity. Only a certain range of frequencies will be able to pass using this LC tank. So the LC tank has got a property of rejecting any unwanted signals outside that passband. So we are going to look at this when we are now looking at the RF amplifier. So types of amplifiers. Amplifiers are just termed in terms of the type of frequencies they amplify. Audio frequency amplifier is called an AF amplifier. It amplifies audio frequency. Then we've got an RF amplifier, which is intermediate frequency. And frequencies, intermediate frequencies is a frequency between RF and AF. So audio frequency amplifier can only amplify audio frequencies. Intermediate amplifier can only amplify intermediate frequency, and then radio frequency amplifier can only amplify a certain range of radio frequency amplifiers. Radio frequencies, sorry. Then we've got a wideband amplifier. The wideband amplifier is termed wideband amplifier because it can amplify a very wide bandwidth, a large number of frequencies. The bandwidth of a wideband amplifier is very large. So, in audio frequency amplifier, we said that it amplifies approximately 20 Hz to 20 kilohertz, and it is any signal within the human hearing frequencies. We also have a hi-fi audio frequency amplifier, which can amplify up to 100 kilohertz. So that's with radio frequency amplifier. So sometimes you might need to connect several stages in series so as to attain very high gain. One amplifier stage cannot be enough to drive certain devices. So multiple stages can be used to increase the gain of amplifiers. Then we've got IF. This concept of IF, we're going to look at it when we're now looking at radio receivers. But in general, what I can say for now is that intermediate frequencies are frequencies below RF but above audio frequencies. And these intermediate frequencies they are used so that we can increase gain at this stage. So you later on find out that when we receive a signal, we receive an RF signal, and then we convert that RF signal to IF signal. At the IF frequencies, that's when we introduce a lot of gain. A lot of gain is introduced at IF frequencies. So here we're given examples of different IF. For example, here we are given an AM radio receiver IF can operate at 470 kilohertz, and then here we are given TV uses 6 megahertz bandwidth, and IF often ranges between 30 to 40 megahertz. And then here we are given also that radar, the bandwidth will be about 10 megahertz that can be used. So these are just examples for our RF amplifiers. Moving on to RF amplifiers. RF amplifiers, we are going to dwell much more on these RF amplifiers in this chapter. So RF amplifiers are basically frequencies from 30 kilohertz to 300 gigahertz. But normally for communication systems, they use frequencies below 100 gigahertz. So all RF amplifiers are tuned amplifier, meaning that they use the LC resonant tank for selecting the frequencies they want to amplify. And it is also important for you to note that just one RF amplifier cannot amplify frequencies, the entire frequency spectrum of RF signals. So you find out you can have amplifying, for example, let's say 1 gigahertz to 10 gigahertz, but it is called an RF amplifier. Another RF amplifier can amplify maybe 10 gigahertz to 40 gigahertz. So there are several RF amplifiers. So the tuned tank is the one that will be able to select the RF frequencies that we want to amplify. So an amplifier should have selectivity, which is select the frequencies that it wants to amplify and give a specified gain for those frequencies within the amplification bandwidth. So here we're given an example, a tuned RF amplifier. If you still remember from your basic electronics, this is an amplifier. The only difference is that here, instead of a collector resistor, we now have an LC tank. This LC tank is now used to select the frequencies to amplify. So you find out at the output here, any frequencies outside the bandwidth of this LC tank is not amplified, but only frequencies allowed by the LC tank here will be amplified. So it is also important for you to remember that the function of R1, R2, and RE, they are for biasing this transistor. Biasing is basically powering the transistor so that it operates in the required region. And also it is important for you to remember that there are 3 regions of a transistor. We've got the cutoff, the active, and the saturation region. So depending on the classes, as we will later on discuss, depending on the class, the function of these resistors is to bias this transistor so that it operates within a certain point of that within a certain point amongst the 3 regions of your transistor. And the capacitor, this is an input coupling capacitor which couples the input signal to the base of the transistor, and the function of the transistor is to amplify your signal. So besides that theory about electronics, as an RF amplifier, this tuned circuit, the LC tank, is the one that makes it a tuned RF, whereby it selects a certain band of RF frequencies to amplify. It can also be variable, whereby you can vary the frequencies that you want to amplify. We can also have what we call an RF double-tuned amplifier. An RF double-tuned amplifier is basically shown here. We've got first tank circuit and the second tank circuit. So we've got two tank circuits, making it a double-tuned amplifier. These two tank circuits, normally they will be tuned to the same frequency, or maybe slightly the frequency might differ slightly, one being a little bit below the operating frequency and the other one being a little bit higher than the operating frequency. So let's take, for example, let's take a look at this frequency response. Here it is just showing us the effect of a double-tuned amplifier. A double-tuned amplifier, the main purpose is for us to produce a flat top here, a flat response. If you recall, we said that a frequency response of an LC tank is basically like this, which means the top here is not flat. So the main purpose of a double-tuned amplifier is to produce a flat response here at the top. So what it does, how it is done, is that the spacing between L1 and L2, this is a transform, the spacing between L1 and L2 determines whether it is loosely coupled, tightly coupled, or critically coupled. If it is loosely coupled, there is no much difference to the of a single tuned tank. And if it is tightly coupled, which means that L1 and L2 are too close together, we produce a more like a M-shaped characteristic. But by critically coupling, which is critically selecting the distance between the two, we can achieve a flat response there. This is something that is done by the manufacturer. It's not something that you can do when you are drawing these circuits. So it is something that can only be achieved by changing the spacing between L1 and L2. So here, this is the most important point. If critical coupling is employed, a more or less flat top characteristic is obtained, meaning that all frequencies within the passband will have a more or less same gain for all those frequencies within the selectivity of the tuned circuit. Then we have wideband amplifiers. So here we basically want to amplify a wide range of frequencies. The bandwidth will be very, very, very big. And this is normally employed in TV signals and radar signals because of the requirement of wide bandwidth. So normally wideband amplifiers, the gain is very low. So to increase the gain, you have to cascade these amplifiers, which means you have to connect so many amplifiers, multi-stages. Then we've got what we call amplifier classes. In amplifier classes, basically we're talking about the biasing, how the transistor is biased so that it operates in a certain region. So we've got those four classes. We've got class A, class AB, class B, class C amplifiers. So let's start with class A. Class A Basically, this is the input signal, this is the output signal. With class A, the transistor is always on. It's always on, meaning that it operates for 360 degrees of this input signal. So when this input is at 0, the transistor is on. When the input is at maximum, the transistor is on. When the input is back to 0, the transistor is on. At minus maximum, the transistor is on. Okay, for the entire cycle, the transistor is always on. So because of that, the transistor loses a lot of power through heat, and hence it has got a very high power loss. And because of that power loss, the efficiency of this class A amplifier is very poor. So you can read on that. It operates in the active region, obviously, for 360 degrees, and the efficiency is normally between 25 to 30%. Moving on to class B. Class B uses two transistors, transistor 1 and transistor 2, at least two transistors. When it uses two transistors, one transistor will only operate for half the cycle, which is 180 degrees. So at this point to this point, transistor A1 is on, whereas transistor 2 is off, as shown by the dotted line. So for this negative part, transistor 1 is now off, whereas transistor 2 is on. So it's actually more like they are helping each other. They are also called push-pull transistors. So once this one is on, this one is off. When this one is off, on, this one is off. They will exchange. Because of that, it actually means we can double the efficiency. The heat losses will be reduced, meaning that the efficiency can now range between 60% and 70%. So let's look at class B amplifier. It uses at least two, and each transistor operates for half the cycle. And then the other part, other half, it will be switched off, therefore reducing wasted power in form of heat. It is also called a push-pull. It operates for 180 degrees. It also has got an efficiency of 60 to 70%. This is where our problem starts with class B amplifier. Operation as 0 DC bias, as the transistor are biased at cutoff. So each transistor only conducts when the signal is greater than the base emitter voltage. If you recall, the base emitter voltage is 0.7 volts for silicon. If it is a silicon NPN or PNP junction, the base emitter voltage VBE is equal to 0.7 volts. So because of that, it actually means that there are times when the transistor will be off. For example, between this point and that point, this transistor will be off. And then it takes time for transistor number 2 also to switch on. So at this point, we have what we call crossover distortion. It's more like handover distortion between transistor number 1 and transistor number 2. There is a time when there is no output signal because of the switch over that happens. So that's one disadvantage of class B amplifier. It introduces the crossover distortion. So in order for us to counter this, we have what we call the class AB amplifier. The class AB amplifier is the same as the class B amplifier. The only difference is that we've got these two diodes. These two diodes enables transistor 1 to remain on whilst this one also is starting to conduct. so that the handover is more or less smooth. So you'll find out that this transistor number 1, will operate for more than 180 degrees. So maybe it can be between 180, for example, let's say it operates for 200 degrees before it switches off. And then this one, there is a time when TR1 is on and TR2 is also beginning to switch. So when this one is now fully conducting, this one switches off. So class AB is in between class A and class C. It doesn't operate for 360 degrees like class A, but it's somewhere in between class B, which is 180 and 360 degrees. So it eliminates the crossover distortion. So it means that the transistor will be on for more than half the cycle, and the conduction angle is between 180 degrees to 360. Then lastly, we've got class C. Class C amplifier, as shown here, operates for less than 180 degrees. It operates from this point to that point of this input cycle. So it operates for less than 180 degrees. And class C amplifier, it conducts for less than half the cycle, which is less than 180. It conducts between 80 degrees and 120 degrees. Because of the amount of time that the transistor is off, it means that most of the time it's actually off. Hence, we've got low heat dissipation through the transistor, meaning very high efficiency. Low power loss, very high efficiency. The reduced conduction angle improves the efficiency, but causes a great distortion. Due to that, class C cannot be used for audio frequencies. It cannot be used for audio frequencies. Audio frequencies, they vary, and sometimes the amplitude will be less than sorry, can I just, okay, so we'll find out there are so many components in an audio frequency signal that makes it complicated for us to use this class C amplifier. Alright, I will stop here for explaining why class C amplifiers cannot be used. Some of these concepts you can understand them when we have looked at concepts like modulation. We see also that with the FM frequency modulation, you can use a class C amplifier, but with AM, first of all, you have to amplify your signal a lot in order for you to use a class C amplifier. So for now, we are saying it is not suitable for certain signals like audio frequency and amplitude modulated signals. So the most common application is for RF signals, and the efficiency goes maximum about 90%. So lastly, we want to look at methods of coupling amplifiers. So we'll start with what is coupling. So here we are shown that we've got a first stage amplifier connected to a second stage. So like we said, in most cases, one amplifying stage is not enough. In order for us to produce a very high gain, we need to connect several amplifier stages. So, in order for us to connect this first stage to the second stage, we need a coupling device. So it is used for multi-stage amplifiers to connect one stage to another. So the purpose of that is to transfer your AC signal, your signal that has been amplified, to the next stage. whereas eliminating the DC bias. So your transistor in the first stage here has got its DC bias. The DC bias is the like I said, is used to power the transistor or to make it operate in a certain region. So when we have got our coupling device, they should be able to discriminate your DC biasing so that it is not coupled to the next stage. So let's take, for example, we've got those 4 types of coupling. So let's look at the resistance capacitance. This is the resistance capacitance. Mainly the capacitor is the one that is doing all the work anyway. So we've got these resistors coupling these resistors and this capacitor coupling the signal to this transistor. So we're simply saying this capacitor here, the main function of this capacitor is to couple the amplified signal from this transistor to that signal. It just passes this amplified signal from this point to that point. At the same time, we've got this VCC here. This is DC. The DC is there as to bias this transistor. So if the DC is allowed to pass to this part, it will change the biasing arrangement. Remember, the biasing also determines the class A, class B, class AB, and so on of this transistor. When it affects that, it actually affects your operation of the circuit. So you want to stop the DC so that it doesn't pass to this output. This DC for this part, the DC for this part, you don't want part of the current flowing to this end. The DC from this part is not supposed to flow to that end. So these two, the DC part is isolated using this capacitor here. So here it says that the coupling capacitor passes AC from the output of the first stage to the next stage, while blocking DC component from the DC bias voltage to affect the next stage. The capacitor CC is the coupling capacitor that connects the two stages and prevents DC interference between the stages. Then we've got the impedance coupling. This impedance coupling uses the inductor and capacitor. It's basically an LC circuit. So this is our DC biasing for this circuit. So this inductor allows the DC biasing for this Q1, whereas this capacitor blocks this DC so that it doesn't go to this part of the circuit. So here we can separate in between. This is the first stage, this is the second stage. So the inductor, basically what it is doing here is to allow DC, it's just allowing your DC to flow to the, so as to bias this transistor. And this capacitor blocks that DC and couples the AC to this output. The coupling network that uses inductance and capacitance as coupling elements can be called impedance coupling network, as shown here. Then we've got the transformer coupling, which is the most common. I think there is also one diagram which we looked at, which had transformer coupling. Transformer coupling, we've got the first stage here. This signal is coupled to the next stage using the transformer T1, and then to the output using transformer T2. So this is a coupling transformer. This transformer also couples to the output. It's an output transformer. So this coupling transformer, the primary is connected to this part of the circuit. As you can see, a transformer, it doesn't have a physical connection. It uses mutual inductance to transfer signal from the primary to the secondary. So because of that, you can easily transfer your signal from this part to that. and then it is fed to the base of this transistor. So there is no physical connection, but the connection is using mutual inductance of the transformer. This coupling method uses the transformer as the coupling device. It is also popular for its efficient and impedance matching. The transformer has got what we call the primary impedance and secondary impedance. So you can connect it in such a way that the secondary impedance matches with the base impedance of this transistor, and the primary impedance matches with the output of this transistor. Then we've got direct coupling. Direct coupling, as you can see, T1 is connected to T2, T2 is connected to T3. There is no coupling device in between. So this is direct coupling, and it is normally used when we want to connect series devices. No coupling devices is used in this case. The direct coupling method is mostly used when the load is connected in series, meaning that there is no issue of impedance matching. Then examples is headphones and loudspeakers. So this is the end of this chapter. For questions, please feel free to contact me. Thank you.